السلام عليكم ورحمة الله، يعطيكم العافية جميعا. المحاضرة الماضية كانت عن Chapter 6 Mechanisms of Heat Transfer. هون راح نحل couple of examples. Example 16.1 و 16.2 they are almost أو لا 16.1 is okay, it has an idea, that's good. The roof of an electrically heated home is 6 meters long, 8 meters wide, 0.25 meters thickness. That's where the heat will transfer through. It's made of a flat layer of concrete whose thermal conductivity is 0.8 watt per meter Kelvin, according to figure 16 for this. So we can see the roof of the house is 8 meters by 6 meters and a thickness of 0.25 meters, which is made of a concrete material that has a thermal conductivity of 0.8 watt per meter Kelvin. The temperatures of the inner and the outer surfaces of the roof at one night are measured to be 15 Celsius degrees inside the house and 4 Celsius degrees at the top surface of the roof, which is open to the atmosphere. For a period of 10 hours, determine first the rate of heat loss through the roof that night, B, the cost of that heat loss to the homeowner if the cost of electricity, since it's electrically heated, the cost of electricity is 8 cents per every kilowatts hours. Every kilowatts hours, that's a unit that's frequently used to represent the thermal energy consumed. Okay, so first, in order to calculate the heat rate, so the heat rate loss would be through the concrete by conduction. So what do we have here? We have delta T of 15 minus 4. Besides, we have the thermal conductivity, so we apply the Fourier's law of heat conduction. So it's simply Ka times T1 minus T2, where T1 represents the temperature inside the house, T2 at the top surface of the roof from the outside, and plug in the values. The L is the thickness, since that's the direction of the heat transfer. In the heat transfer course, we will limit ourselves to the case of one spatial dimension heat transfer, one spatial dimension. Okay, so we have, and so neglect the heat transfer in the other dimensions, which are here along the length of the roof and the width, the length and the width of the roof. So the heat rate is simply 1690 watts, which is equivalent to 1.69 kilowatts. In order to calculate the amount of heat lost, simply that equals to the heat rate times the time period, which is mentioned here to be 10 hours. So times 10 hours, that gives us the amount of heat in kilowatts hours. So that's 16.9 kilowatts hours. The cost, every 1 kilowatts hours cost 8 cents. So that makes the 16.9 kilowatts hours cost $1.35. $1.35. Let's see other examples. Okay. This example to measure the thermal conductivity of a material. Okay, a common way to measure the thermal conductivity of material, which is, by the way, this there's one experiment in your thermal fluid sciences lab that's related to measure the thermal conductivity of a material, but I believe the procedure is a little different from the one here in example 16.2. So what do we have here? Measuring the thermal conductivity of material that's sandwiched an electric thermofoil heater between two identical samples of the material, as shown in the sketch here. So these are the two samples. This is the electric thermofoil heater. Now the heater heat the electricity power, the electrical power, which is converted to heat, will be transferred equally to the two samples. The thickness of the resistance heater, including its cover, which is made of thin silicon rubber, is usually less than 0.5 millimeters. A circulating fluid such as tap water keeps the exposed ends of the samples at, which are here, this top and the bottom cooling fluid, keeps the exposed ends of the samples at constant temperature. The lateral surfaces of the sample are well insulated. So here it's well insulated from this and this. So the heat will transfer only in one dimension, which is this dimension. Okay, to ensure the heat transfer through the sample is one dimensional, as we mentioned. Two thermocouples are embedded into each samples as shown here. Two thermocouples at each sample, some distance L apart, and differential thermometer reads the temperature drop delta T across the distance along each sample. When steady operating conditions are reached, the total rate of heat transfer through both samples becomes equal to the electric power drawn by the heater. So the electric power will be equally transferred into the two samples. In a certain experiment, cylindrical samples, so these are cylindrical in order to calculate the cross-sectional area, of diameter 5 centimeters and length 10 centimeters. This is the length and this is the diameter. And the two thermocouples in each sample are placed 3 centimeters apart, so the L is 3 centimeters. The electric heater is observed to draw 0.4 amperes at 112 voltage potential, and both differential thermometers read a temperature difference of 15 Celsius degrees. The delta T is 15 Celsius degrees. So the electricity, as we mentioned, the electric power equals simply as voltage potential times the electric current. That gives us 44 watts. It will be equally distributed to the samples. Okay, so every sample will have half of this electric power, so that's 22 watts. The cross-sectional area of the sample is 1 pi d squared divided by 4. That gives us this value of the cross-sectional area. So now, according to Fourier's law of heat conduction, Ka times delta T divided by L, rearrange the equation and solve explicitly for the thermal conductivity. It's found to be 22.4 watt per meter Kelvin. Okay. All right. Let's move to, example 16. For measuring the convection heat transfer coefficient, here we have a 2 meters long, 0.3, we have a 2 meters long, 0.3 centimeters diameter electrical wire extends across a room at 15 Celsius degrees. The heat is generated in the wire as a result of resistance heating, and the surface temperature of the wire is measured to be 152 Celsius degrees in steady operation. Also, the voltage drop and electric current through the wire are measured to be 60 volts and 1.5 amperes. Disregarding any heat transfer by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. Okay, that's good. Here, it's obviously it's a convection problem in order to calculate the convection heat transfer coefficient. So here, the surface is assumed to have a constant temperature of 152 Celsius degrees. Now, we apply here the procedure to solve this example. We apply the Newton's law of cooling between the surface of the electrical wire and the adjacent air, which is at temperature 15 Celsius degrees. We need to calculate the surface area of the electrical wire. We have the diameter, we have the length, of the wire, so we can calculate the surface area and apply the Newton's law of cooling. First, in order to calculate the heat rate, then it's equal according to the energy balance at steady operation to the electrical energy generated in the wire. That's the voltage times the current, gives us 90 watts. The surface area is pi dl by disregarding the ends. So that's pi dl, and it equals to this value. According to Newton's law of convection, the Q dot, which is the same as the one here, according to energy balance at steady state conditions, that's H times E sub S times T sub S minus T infinity. This Q dot convection is equal to the 90 watts. Rearrange the equation and solve for the convection heat transfer coefficient. It's found to be 34.9 watt per meter square Kelvin. Let's move to another example. Let's check this example 16.5. It tells us that there's this girl is standing in a room where there's the walls of the room has a temperature of what? The walls of the room, the room is maintained at 22 Celsius degrees. Okay. Okay, the person standing in a room, the room is maintained at 22 Celsius degrees, while the walls, floors, ceilings of the house are observed to be an average temperature of 10 Celsius degrees in winter and 25 Celsius degrees in summer. Determine the rate of radiation heat transfer between this person and the surrounding surfaces if the exposed surface area and the average outer surface temperature of the person are 1.4 meters square and 30 Celsius degrees respectively. Okay, the net rate of radiation heat transfer is given through this equation as we explained in the previous lecture. Epsilon times sigma times surface area times Ts to the power 4 minus T surrounding to the power 4. In the winter, everything remained the same except between the winter and the summer, we change the surrounding temperature. In the winter, that's 10. So we need to convert this to Kelvin. So it's plus 273, as shown here. While in the summer, it's 25 plus 273. The other parameters remain the same. The emissivity for the person, that's for the human skin, we get it from table 16.6. As we mentioned in the previous lecture, that's 95%. So calculate the net radiation heat rate in the winter from the body of the girl is 152 watts, while in the summer it's 40.9 watts after plugging in the value for the surrounding as 25 plus 273 Kelvin in the summer. Okay. Here in simultaneous heat transfer modes, again, as we mentioned at the end of the previous lecture, the heat transfer mechanisms in practice, they occur simultaneously. So the same previous example, but now we want to calculate the total heat rate. So the total heat rate, since there's a moving flow air in the room, which is at temperature of 20 Celsius degrees. The person now has a surface area of 1.6 meters square and average surface temperature of 29 Celsius degrees. The convection heat transfer coefficient is taken to be 6 watt per meter square Kelvin. We want to determine the total rate of heat transfer. Obviously, here the heat transfer rate, there is conduction through the air, but it's negligible compared to the convection, the radiation. So the heat rate is through convection and radiation. The convection is through Newton's law of cooling, H times surface area times the temperature difference between the surface and the free stream. That's found to be 86.4. while for it's here assumed that the surrounding is also at 20 Celsius degrees, same as the room air temperature. So we calculate the net radiation heat rate from the outer surface of the person's body. It's found to be 81.7 watts. The total is the sum of these two, and that gives 168 watts. 168 watts. Okay. This last example, it talks about the heat transfer between two isothermal plates. Consider steady heat transfer between two large parallel plates at constant temperatures T1, T2, 300 and where they are of temperatures 320, 200 kelvins. The distance between the two is of 1 centimeters. The distance between the two plates is 1 centimeter. Assuming the surfaces to be black, so their emissivity is 1, their emissivities are 1. Determine the rate of heat transfer between the plates per unit surface area, assuming the gap first is filled with atmospheric air, B evacuated, C filled with urethane insulation, and D filled with super insulation that has an apparent thermal conductivity of this value. Let's discuss, before starting solving these different conditions, let's first start by discussing these different cases. First, if it's filled with atmospheric air, okay? If it's filled with atmospheric air, then we will have the heat will transfer through. Assuming this air is still, it's not moving, then there will be no convection. And the heat will be transferred through conduction and radiation. B, if it's evacuated, the only heat transfer mechanism that can occur without intervening medium is the heat transfer by radiation. So that would be only by radiation. C, if it's filled with urethane insulation is considered as opaque material, so there would be no radiation. And of course, there's no convection since there's no fluid motion. It's just solid. So it would be just conduction. D, similarly, it would be just conduction. So go to A. A, we will have conduction through the air. We get the thermal conductivity of the air. We find that the conduction heat rate is 219 watts, while the radiation heat rate is 369 watts. The total is the sum of the two. No convection since the air is not moving. B, when the space is evacuated, so it's only radiation, and it's already calculated from the previous case. C, if it's an insulation urethane material, so there's no radiation, no convection, and it's only conduction. No radiation because it's opaque and it will not allow the radiation to occur. It's an opaque solid material. Similarly for D, but now the thermal conductivity is much less, so we can see the heat rate reduced substantially to 0.2 watts. 0.2 watts. Okay, so that's all. Except we probably can check this example 69. It's an interesting example since it's for the incident radiation. So a thin metal plate is insulated in the back and exposed to solar radiation at the front surface. The exposed surface of the area has an absorptivity of 0.6 for solar radiation. If the solar radiation is incident on the plate at a rate of 700 watt per meter square, the surrounding air temperature is at 25 Celsius degrees. Determine the surface temperature of the plate when the heat loss by convection and radiation equals the solar energy absorbed by the plate. Assume this is a steady conditions. Assume the combined convection and radiation heat transfer coefficient to be 50 watt per meter square Kelvin. Wherever we see the combined, that means convection and radiation, that means that the surrounding and the free stream temperatures are equal. So that means this incident radiation equals to the heat leaving the surface of the plate by radiation and convection. So 700 watt per meter square times the area equals to the heat rate by radiation and by conduction together. So that's E dot gained, it's by the incident solar radiation equals to the E dot lost by the combined radiation and convection, according to this equation here. We can see that we don't need the surface area, it will cancel from both sides, and rearrange the equation and solve for the surface temperature. We'll find it equals to 33.4 Celsius degrees. اوكي، that's all. يعطيكم العافية. نشوفكم قريبا ان شاء الله.